are welcome to section 5 of unit 1. Let's look at the section objectives. By the end of this section, you should be able to 1. Find the Cartesian product of any two given sets. 2. State the properties related to Cartesian products. And 3. Prove the properties in 2 above. We start this section by looking at what we call ordered pairs. And in mathematics, an ordered pair A, B is a pair of mathematical objects. The order in which these objects appear in the pair is very, very important. So if you have the ordered pair AB, it is totally different from an ordered pair which is BA. They can only be equal if A is equal to B. Ordered pairs can also be called two tuples or sequences of length 2. Now if you have an ordered pair A, B, the first entry, which is A, and the second entry, which is B, can also be called coordinates, first coordinates and second coordinates, or they can also be called left and right projections of the ordered pair. Cartesian products and binary relations, and for that matter functions, are mostly defined in terms of ordered pairs. So if you have an ordered pair 3, 5, it is not the same as 5, 3. The two mean totally different things. The next thing to consider is the Cartesian product. The Cartesian product, which is also called product set or set direct product or cross product of two sets A and B, is the set of all ordered pairs A, B, where A is found in the first set A and B is found in the second set B. Let's look at the definition. The Cartesian product of two sets A and B, denoted by A cross B, is the set A cross B is equal to, in parentheses, ordered pair A, B, such that small a is a member of the set A and small b is a member of set B. Note, however, that the elements A, B of A cross B are ordered pairs. Let's consider example 1 and take a look at the sets A, which is made up of 2, 3, and 4. Then set B, and it is made up of 4, 5. Find 1. A cross B, 2. B cross A, and C, B cube. Let's look at the solution. The first one, A cross B. So you have your parentheses, and in the parentheses you get the first pair by taking the first entry of the first set against the first entry of the second set. So the first ordered pair we will have will be 2, 4. Then the next one will be the same 2 against the second entry. So 2, 5. So we are done with 2. We come to 3. So we do 3, 4, and then we do 3, 5. Then we move to 4. And we do 4, 4, and we do 4, 5. That forms the A cross B. Then when you come to the second one, which is B cross A, this time round we will start with the elements in B and match them with those in A. So the first one will be 4, 2, then 4, 3, then 4, 4. Then we move to 5. Then we have 5, 2, 5, 3, and 5, 4. So that gives you the solution for B cross A. So you see that B cross A is totally different from A cross B. Then we go to B cube. So what B cube means is we are going to do B cross B cross B. And so we will repeat the set B 3 times. So the first one will be 4, 4, 4. Then we have 4, 4, 5. Then we have 4, 5, 4. 4, 5, 5. We are done with 4. So we move to 5. And so we have 5, 4, 4, 5, 4, 5, 5, 5, 4, and then 5, 5, 5. Let's look at the first theorem under the Cartesian product. And it says, for any set A cross empty set is equal to empty set. Conversely to empty set cross A is still equal to empty set. We will want to prove this theorem. So suppose the ordered pair A, B is a member of A cross empty set. Then it means that A is a member of set A and B is a member of the empty set. But B being a member of an empty set is not possible. And so A cross empty set is equal to an empty set. Theorem 2. For any sets A, B, and C, A cross bracket opens B intersection C bracket closed is equal to bracket opens A cross B bracket closed intersection bracket opens A cross C bracket closed. 2. A cross bracket open B union C bracket closed is equal to bracket opens A cross B bracket closed union bracket opens A cross C bracket closed. The next one, bracket opens A intersection B bracket closed cross C is equal to A cross C intersection B cross C. The last one, A union B into bracket cross C is equal to bracket opens A cross C bracket closed union bracket opens B cross C bracket closed. So if you look at these theorems, you will see that they are mostly about the distributive property, where you have cross being distributed over intersection and cross being distributed over union, or you have intersection being the opposite and then union also being the opposite of the first two. So we are going to prove the first one, and then it will help you to be able to prove the rest of them. So suppose that the ordered pair AB is a member of set A cross bracket opens B intersection C bracket closed. Then it means that A can be a member of set A and then B will be a member of B intersection C. This means that A is a member of set A and B is a member of set B, and the same B is a member of set C. And that implies that the ordered pair AB is a member of A intersection B, and the same ordered pair AB is a member of A intersection C. And so AB is a member of bracket open A cross B bracket closed intersection bracket opens A cross C bracket closed. Therefore, every element in the ordered pair AB that can be found in A cross bracket open B intersection C bracket closed can also be found in bracket opened A cross B bracket closed intersection bracket opens A cross C bracket closed. We therefore conclude that A cross bracket open B intersection C bracket closed is the same as bracket opens A cross B bracket closed intersection bracket opens A cross C bracket closed. Let's now look at these two definitions. The first one, a binary relation from set A to set B is a subset of A cross B. The second definition says a binary relation on set A is a subset of A cross A. We will illustrate this definition with the example below. Consider the set A, which is 2, 3, and 4, and the set B, which is 4 and 5. Then we can define the following binary relations from set A to set B. Similarly, if set A is equal to 2, 3, and 4, then we can define the following binary relations on set A. Considering the A, the first one, some of the subsets that you can get for A cross B are 2, 4. You can also have 2, 5. You can have 3, 4. You can have 3, 5. You can have 4, 4. And you can have 4, 5. So those are some of the subsets that you can get from A cross B. So these subsets can be plotted in on a graph. So for example, you can plot 2, 4 on the graph. You can also plot 3, 5 on the graph to get the first relation. Another relationship which we can find from that, which we can call relationship 2, is 2, 4, 3, 4, and 4, 4, which you can see on the plotted graph. The third relationship which we can also get is 2, 2, then we can have 3, 3, and we can have 4, 4. Another relationship which we can look at is 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4, 4, 2, 4, 3, and 4, 4. We look at some more definitions. For any two sets A and B, the number of elements in A cross B is magnitude A cross B, which is equal to magnitude of A dot magnitude of B. This means that there are exactly two exponents A cross B magnitude relations from A to B. So if you want to find the number of relations from A to B, you do 2 exponent magnitude of A times magnitude of B. Let's look at the following examples. If set A is equal to 1, 2, 3, 4, 5, and set B is equal to W, X, Y, Z. How many elements are there in the relation A cross B? Question 2. Suppose that the set A is equal to 1, 2, 3, and the set B is equal to 3, 4, 5. Find A cross B. B, the number of relations from A to B, and C, the number of relations on A. Let's look at the solutions. There will be 20 elements in A cross B. That is 5 times 4. And so the number of elements in the power set of A cross B will be given by 2 exponent 20. And that will give you 1048,576. If you look at the second question, the A will be given by 3 cross 3, which is 9. Then the B will be given by 2 exponent 3 cross 3, which is 2 exponent 9. And that will be 5, 1, 2. And the last one will also be 2 exponent 3 cross 3. And that will be 2 exponent 9. And that will be 5, 1, 2. Thank you.